Okay, hello everybody. Good morning, all of you. So we'll start with today's quote by Michael Jordan. And he says, obstacles don't have to stop you. If you run into a wall, don't turn around and give up. Figure out how to climb it, go through it, or work around it. Because in our journey, nothing will be smooth, and always everybody, we find obstacles, we find problems, we find difficulties and all. And the people who continue and find out solutions and go further up, they only can reach the goal. Okay, so nothing should stop us. And today is the birthday of the great Louis Braille. I think everybody is familiar about him. So who is he?
It's a method of reading for blind, sir.
Yeah, so he has found the method for method of reading for the blind. Okay, and he is also a blind person, but not by birth. During accidentally, he lost his sight, and okay, he developed a tactile form of printing and writing known as Braille, since widely adopted by the blind. He himself knew blindness from the age of 4, following an accident while playing with a tool. Okay, and all tool-like thing he played, and somehow by accident he lost his sight. In 1821, while Braille was all at a school for the blind, a soldier named Charles Bobbier visited and showed a code system he had invented. Okay, actually before him, so there is another person who has invented the system, but he has modified and updated. So this system called night writing had been designed for soldiers in war trenches to silently pass instructions using the combinations of 12 raised dots. And the young Braille realized how useful this system is. The system of raised dots could be. He developed a simpler scheme using 6 dots. Okay, concept is that, but he has reduced the number of dots, and with 6 dots, he has developed the long list. In 1827, the first book in Braille was published. Now the blind could also write it for themselves using a simple stylus to make the dots. Okay, so this is the great person, Louis Braille. I think if you have drawn drawing here in the first year, you have drawn drawing here in the first year.
Yes, sir. Part of us have done, sir.
Okay, actually, those drawing sheets we are supplying to a blind school. All the drawing sheets we collect here, and we are supplying so that they can use it for daily practice. Right? There will be some costly sheets for exams, but for practice and these things, they always request us to have the sheets. Unfortunately, the last 2 years we could not supply them, but usually I do that. I request all the CRs to collect the papers, and we used to supply them to the blind school. Okay, so coming to the revision of class 1, last class we were discussing about what is the philosophy of CFD, what are the 3 dimensions of fluid dynamics like analytical, experimental, numerical, and all, and what is D'Alembert's paradox, what is Planck's boundary layer theory, and what is von Karman vortex treat. And see, we have seen the failure story of Tacoma Bridge. And not only that, actually, if you stand near any electric pole or phone wires, so near the pole, if you keep your ear, so there will be humming sound of the wires. That humming sound also comes because of the von Karman vortex treat, because the air will be there going on the these are like cylinders, long cylinders, right? So they form vortex treat, and because of that the wires vibrate and they give a humming sound like that. And then success story of Himat, ICBM story of failure and success. We have seen normally as the speeds increase, the nose should be as sharper as possible to have a streamlined flow. But when it comes to supersonic flows, it is better to have a rounded nose so that you will have a detached shock, and it can withstand higher temperatures, because highest temperatures can be dissipated uh, to the space between the shock and the body. And then we have seen some animations of CFD results, and we have seen experiments versus simulations, how we can simulate almost of the same clarity as experiments. And we have seen what is CFD, where do we use CFD, why to use CFD, the prerequisites of CFD, what are the subjects we need, and what are the textbooks for CFD, what is the scheme of evaluation, and authors of reference books on CFD, and NPTEL courses on CFD, journals of CFD, commercial packages on CFD, and all these things I have given in the last PPT, just to you go through them, and few milestones in the early history of CFD, and the people who are the pillars of CFD. A lot of people names I have given, but I didn't tell you what are their contributions, because through the course you will come across many of the people, and once the course is over, you will know what is the contribution of each person. If you are really interested, you can go through Wikipedia and see the contribution of each and every person. Okay, so these are the things we have studied in the last class. And today, in this class, we will see what is the software development process. It is a second chapter from Numerical Methods by Chopra. I think you got all my mails. Have you got my mails?
Yes, sir.
Yes, sir.
So one mail is having books, right? So Anderson book, Hoffman books. They are the things mainly we follow throughout the semester. But first one or two classes, like today's class, I will take one chapter from Numerical Methods by Chopra, and another book also by Chopra and Kennel for MATLAB, and Rudra Pratap also is there for MATLAB. So whoever is interested and can learn MATLAB from these books, and you can feel comfortable. I think, have you attended the workshop normally conducted by our college? MATLAB. Is it conducted?
Not yet, sir.
Not yet.
Last year it was conducted.
Okay. Usually Harikumar sir usually conduct MATLAB workshop like thing. So if he conducts, you just attend it, so that you can anyhow, because C++, MATLAB also is a similar language. Only thing is few syntax things will be different. Okay, briefly we will see the detailed syllabus. I have sent you detailed syllabus, lecture schedule, and last PPT notes and video, all those things I sent you. If there is anything you could not get, you just tell me, right? And today's class, we will see what are the course outcomes of CFD, description of chapters of CFD, some results of CFD in various fields, and the software development process, approximations and round of errors, significant digits, error definitions, and chopping. So we will see these things today. And what are the course outcomes? Once you complete the course, this is all these things, first few slides are there in the detailed syllabus that is there in your website, and also the file I have sent you. And so you should be in a position to develop mathematical models for flow phenomena and analyze mathematical and computational methods for fluid flow and heat transfer simulations, and solve computational problems related to fluid flows and heat transfer, and evaluate the grid sensitivity and analyze the accuracy of numerical solution, and evaluate flow parameters in internal and external flows, and develop flow simulation code for fluid flow and heat transfer problems. Okay, these are the things you are expected to be comfortable and familiar once you complete the course. And the first chapter, it deals with history and philosophy of CFD. CFD as a design and research tool, applications of CFD engineering. Okay, that we have discussed in the last class. And today's class, we will see programming fundamentals, MATLAB programming, numerical methods. So the next chapter, it is, okay, as I told, this programming fundamentals is from numerical methods by Chopra, and this MATLAB programming is another book by Chopra. MATLAB is there, and numerical methods again from the same book. And governing equations of fluid dynamics we get from Anderson. Okay, so again, all these things in your BTech, second year in fluid mechanics, but we will do in a detailed way, and we'll try to understand the physical insights into the equations. So this chapter is from Anderson. And then mathematical, and from here onwards, most of the things come from Hoffman. There are 3 volumes are there, first volume, right? and mathematical behavior of partial differential equations. I think this also you have learnt in your mathematics, but again, we will go in more detail. Classification of partial differential equations, methods of determining classification, that is which class of family this equation becomes, and general behavior of hyperbolic, parabolic, and elliptic equations. Okay, this is the first chapter of Hoffman first volume. Okay, and then we'll see what is the basic aspects of discretization and how to discretize the equations. So you might have come across like finite difference method, finite element method, finite volume method, and all those things. So what we do is we discretize the equations in one of the method, that is partial differential equations are converted to ordinary algebraic differential equation. Algebraic equations. Differential equations are converted to algebraic equations. That's what we do. So the CFD, that is the first thing we do. We will see the CFD overview. There is a top class right there. The whole thing, what we do in CFD, right? We will discuss in that class. Okay. So first we have to know the problem, what is the problem, and then we have to understand what are the governing equations, and we have to simplify them by various assumptions. And those simplified equations, finally partial differential equations I have to use one of these discretization methods like finite difference or finite volume or finite element, and we convert them into algebraic equations. Okay, so that is what is called a finite difference equation. So we convert them. This is discretization. And then, as I told, there are classification of partial differential equations like parabolic, elliptic, and hyperbolic. So here we concentrate on each type of family of equations, and we see what are the various methods of solving them. Okay, so first we discuss parabolic partial differential equations, how to solve them. Various methods are here. And then there is what is called as stability analysis. So there is error analysis, stability analysis, whether a particular scheme is stable or not. Stable means actually where I was talking about converge. Okay, where sometimes the scheme may not converge in the iteration process, right? You have taken some initialization and then you are updating, and the error, instead of decreasing, if it increases, it is diverging, and if it is decreasing, it is converging. So when I use a particular scheme, I have to see whether it is converging or not. For that, I have to check do the error analysis, stability analysis, and all those things. So that comes here, and then elliptic equation solvers, and then hyperbolic equation solvers. So once you understand simple equations, we will take the simplest parabolic, elliptic, hyperbolic equations. But the Navier-Stokes equations will have all of them together. Okay, then we go for that. This is what is called a scalar representation of Navier-Stokes equation. This is one-dimensional Navier-Stokes equation, how to solve it. And then we concentrate on incompressible Navier-Stokes equations. Okay, that we do. And in the last chapter, we discussed about compressible Navier-Stokes equations. And in between, we discuss about grid generation and all. So grids with appropriate transformation, and structured grid generation, and unstructured grid generation, and then finite volume method for unstructured grids. And the numerical solution of this is compressible flow, right? Quasi one-dimensional nozzle flow. So like this, these are the various things. It's a little bit huge syllabus, but the intention is once you complete the course, you should be in a position to understand any paper that you see from the literature. So if you want to do project on that, and if you come with a paper, and you should be in a position to feel comfortable and familiar with all the terminology that is there in that paper, published paper. So that's what the intention is. Okay, some results of CFD. These are taken from Anderson. That is, once you do the analysis and all, you are going to do the post-processing. Already I have shown you a lot of results, like animations and all. Similar to that, there are various other ways of presenting the post-processing. Like, okay, you can have the streamline pattern when there is a flow over a aerofoil. And if it is a laminar flow, how it comes, right? So, and yeah, you can have XY graphs, the lift and drag, or the when there is a flow or the aerofoil, how the lift and drag are. And then the flow field, how the flow field is, are the pressure contours, velocity contours, temperature contours, Mach contours, all those things you can get. So the pressure coefficient over upper and lower surfaces of these aircraft. And then computational mesh also you can show, right? This is the mesh and this is the flow. Right? And mesh on the internal and external regions of a jet engine. All these are taken from Anderson book. It is on, see, in 6th chapter. Right? And if there is liquid iron flowing into a mold from 2 gates at 3 different times, okay? So an unsteady flow, that is initially how it is, and after some time how the flow is, and after some more time how it is, right? That so an unsteady flow at different times if you take, so you can find out how the molten liquid is flowing through the gates. And then streamline pattern for flow into a chemical vapor deposition. So it is flow is coming like this. So a small slit here. So because of that, it diverts here and there will be vortices generated here. We can find out all these types of patterns. And mud and water layers in a mud trap, with the mud being suctioned at the bottom left. So if you are sucking mud, how it goes. And velocity field for the flow through a furnace. And airflow pattern in an office building like HVAC I was talking. So you can see how the pattern is. And based on this, you can see where there is more flow, where there is less flow, where it is better to keep the instruments, where it is better to keep our seats and all to sit. So like that you can understand. And meshing over a submarine and the flow pattern in the stern region, right? How the flow is, and you can see the mesh. And many times people have normally say when you are using a package, commercial package, okay, what is that big you have done? You have just given the input and got the output. It's not so easy, right? This mesh generation itself, it will take very, it's very tough and it takes a long time because you have to take appropriate mesh. And for that, actually, you have to have the physical understanding, and you have to know where the mesh should be clustered, where should it be coarse and all. Because unless you know the physics of the flow, you cannot find out what mesh is more suitable for a particular problem, right? So whenever there is gradients, the property gradients are large, I have to take fine grid there. There should be more number of points. It's like if you are doing an experiment, if there is a some change in your property, I have to take some more readings in between, right? So that I can draw a graph, I can understand how it is changing. So in that way, if you have a boundary layer, I should have more number of grid points in the boundary layer because the gradients are very large. In the outer region, I can have less. So if you want to have fine detail, actually, what is the difference between an exact solution and a approximate solution is analytical solutions, which are exact solutions, are continuous solutions. Okay, so velocity is given as a function of x, y, z. Pressure is given as a function of x, y, z. And temperature is given as a function of x, y, z. So at any x, y, z point, I can find out the value of the property. Okay, that is continuous functions. But here it is not like that. We are going to, at discrete points. We are discretizing it at different nodes. I am calculating it. Okay, so we'll get the solution at the discrete points. And so if I want to have finer details, so wherever there is changing is taking place, I want more number of values there, and I should have fine grid in those particular regions. Are you able to understand what I'm telling?
Yes, sir.
Yeah. So the thing is, if I want to have close to a continuous solution, I should have fine grid everywhere. And then what happens? There will be millions and millions of grid points, and at each point I have to calculate and I have to do the iterations and all. It takes very long time, and it needs lot of space. So I cannot have fine grid like that. But if I have a coarse grid everywhere, what happens? Wherever I want finer details, I will not get it. But the solution can be calculated somehow, but I will not get, suppose the drag I want, the friction drag and all. I cannot calculate it will not give the velocity gradient, current gradient at the surface. So the finer grid puts the load on a computer, and the coarse grid will not give you the details. So I have to have a method of having grid, a variable grid, in such a way that I can have fine grid like this wherever there are more gradients, and coarse grid wherever less gradients are there, so that I will have better solution and the reasonable load on the computer. Okay, so that is it. Okay, now we'll see a general software development process. If you are given to develop a code, suppose for your project, some three people or some 10 people may be working in a company. Okay, so how to go about it? Okay, so before going to that, we will see how the evolution of computers has taken place. So we have zero generation, first generation, second generation, third generation, like that generation of computers. And before 1951, the computers are called zero generation computers, which are manual and mechanical, like Pascal's mechanical engine is there. And then first generation computers, when they are vacuum tubes are invented. So we have got first generation computers from 51 to 58. These are computers with vacuum tubes. And actually, when we were in BTech, we had electronics lab. We worked with vacuum tubes, but now they are completely outdated. And then the transistors came, and second generation computers came, like computers with transistors. Okay, 58 to 64. And then third generation computer, when these transistors are could be put in an integrated circuit, some lakhs of transistors in a small chip, right? So then we got the third generation computers. So in nowadays, when I was in final year, we got a computer in our university, and there was a big building given for the computer. Okay, it occupies so much of space, and now we are having whatever we could do with that such a huge computer. Now we are doing with a small laptop computer or desktop computer. Okay, then we got what are called as microprocessors. So we got fourth generation computers from 71 to 2010, and then we got very large scale integration. Okay, these integrated chips, we call them as small scale uh, integration, and medium scale integration, large scale integration, and very large scale integration. Now we are using these fifth generation computers, which are using very large scale integrated microchips or microprocessors. And then we are expecting to have sixth generation computers in future with supercomputers with artificial intelligence. Okay, this is evolution of computers. Okay, we have the in a software development cycle, we have to plan first, and then analyze, then design, then implement, then test and integrate, and then finally maintenance. And upgrading of your software like Windows or this thing, that is what is called as maintenance. After every few days, we will get an upgraded version, right? So that if there are any problems given by customers, they will be eliminated and they will be updated and upgraded. So what is the stepwise process for writing a program? So first we have to define a problem. Then we have, this is actually somewhat for your even CFD also, but that will be a little bit different. There also a stepwise algorithm we will see for a CFD problem, but it is for a general writing a software program problem. Okay, so defining the problem, then problem formulation, and once you formulate it, we have to design an algorithm. Okay, what do we mean by algorithm? A stepwise process, right? Developing the underlying logic of the program in logical stepwise procedure. So that we call it as algorithm. And then we have to draw a flow chart. These things you might have studied in your programming class in the first year. So we have to draw graphical representation of the algorithm. If I write number of steps like that, it is for another person, it will be boring and difficult to understand. But if you write it in a graphical way, okay, first this step and then whether this or this like that, if you draw in a flow chart, it will be easier to understand. So that is graphical representation of the algorithm. then we call it as a pseudocode. So if you take any books of algorithms and all, and it will not give in C language or MATLAB language or Fortran language. It will give a generalized code, and so that can be converted to any high-level language. That is called a pseudocode. Okay, so this uses code like symbols with fundamental control structures. Then program composition, that is writing of that pseudocode into higher level language. So writing the program in high level language is called as program composition. And once you write the program, then you have to debug it. Okay, so we have to correct the errors, whatever are coming on. So that is called as debugging. That is eliminating, bug is an error, and debugging is elimination of errors. Deals with correcting known errors. And then I have to test it. Okay, once I eliminate errors, I'm going to get some result. But that result, whether it is right or not, yesterday we was talking about validation and verification. Okay, that's what we call testing. So with varied data to make it more reliable. Okay, so once we test it, then we have to document it properly. So even if I give you the program, you should be able to understand it, and you have to be able to for your application. So for that, we have to have documentation. Like suppose if I want to use ANSYS or Fluent or something like that, I have to have documents, manuals available with that. I have to understand each and everything. So unless they are supplied, many times we will not understand what exactly it means. It should have user-friendly thing, right? Either it must be graphically user-friendly, or it can be uh, what is that called as GUI, right? Graphical user interface should be good, right? And then storage and maintenance, that is backing up and upgrading, as I was telling. So these are the various things are needed for any program to work on and to make it make a market for it. So what is programming style? Okay, when you are given a very big program, it's like if you are in charge of an institute, like you have to conduct convocation, right? So how do you do it? I have to simplify it. So there are various types of designs like modular design, top-down design, and structured design. Okay, what do you mean by modular design? Divide the program into sub-programs or modules that can be developed and tested separately. It is just like if you want to conduct a convocation, you should have various committees will be there. Okay, inviting committee and organizing committee and transportation committee, arrangement committee, all those things like will be there like that, so that it can be divided into like that. In the same way, we divide the program into number of modules. And as I told, it will be a teamwork, and each group will be working with different modules, and each can be tested separately. And then that is one method. And another top-down design, okay, begins with the most general statement of the program's objective, and then successfully divides it into more detailed segments, and the design proceeds from general to specific. Okay, so that is top-down design. And then structured design, it follows a set of rules that prescribes good programming style that results in a superior, elegant, and easily understandable code. Okay, this is very important. Actually, there are a number of different programming languages are there. Like first basic language was there, BASIC, right? Beginners all-purpose instructional code, that is basic. And then we have Pascal, Fortran, and all those things. So this basic and Fortran, they are not structured codes. Okay, so what happens is if I write a program and I execute it, but if you ask it, I will give it. You will not understand anything. There will be jumping of from here to there, there to here, like that. That is what is called as unconditional go to. Okay, so there is one particular statement: go to 25, go to 30, like that. So I will go there from there to here, like that. So there it is not completely unstructured, which is difficult to understand. Later, this Pascal, C, MATLAB, all these are called structured designs. When is it stopped? Okay. Now is it okay?
Yes, sir. Now it's okay.
Okay, I don't know how it has come out. Okay, again I have to share. Huh? Okay.
Yes, sir.
Now it's okay.
Yes, sir.
Yes, sir.
Yeah. So have you did I show? Have you seen this slide?
No,
No,
sir.
sir.
Okay, this previous one. This
Yes,
you
sir.
have seen.
Yes, sir.
Okay, algorithm design. So there should an algorithm should have satisfy some characteristics. One is it should be deterministic. Whoever uses it, it has to give the same result. Okay, so each step must be deterministic, and that is nothing is left to chance. The final result cannot depend on who is following the algorithm. And the next one, it should end in finite number of steps. There should not be an infinite loop. Okay, it should not go. It should not be open-ended. Like as I was, I don't know whether you the connection was there at that time. So if you are written a program to find out prime numbers, so you cannot write a program which can find out all the prime numbers, because then it will be infinite. It will not end. Okay, so I can find out the prime numbers from 1 to 100, or some 5,000 to 10,000, or up to 10,000, like that. But it cannot find out all the prime numbers just like that. So it will become an open-ended one. So my algorithm should not be like that. And the algorithm must be general enough to deal with any contingency. Okay, like as I was telling, if you write a program to find out the roots of a quadratic equation, right? So it should work. The data will be ABC, ax square plus bx plus c equal to 0. So you want to give the inputs ABC and to get the roots out of it. So whatever type of values ABC you give, you should be in a position to get the result. Okay, sometimes you will write for real values, and the data may say finally it may say give an error that there is a negative you are trying to find out root of a negative value. So there may be ABC values which give you imaginary values. So that it has to take care of. So it has to find out the root, and when the value b square minus 4ac, based on whether it is positive or negative, it has to find out the real values or imaginary values. So your program should take care of that. So any type of data, it should be in a position to deal with. So that's what many times what happen is your data will you have tested, it has worked, and you thought it is working, and when you sell it, so another person may use it, and for his data it may give some problem. Okay, there may be some divided by zero value, the error may come, or root of a negative value may come like that. So it should be general enough. And also, suppose I write a program to find out the inverse matrix for a 3 by 3 matrix, inverse of a 3 by 3 matrix. And so I told I have written for 3 by 3. But another person want to have for 4 by 4. And then it will not work. But if I can write it for n by n matrix in general one, and if the program asks what is the value of n, and it can work out for any size of matrix. So it should be more general. And then flow charting, how the flow chart should be. It should be a visual and graphical representation of an algorithm. The flow chart employs a series of blocks and arrows, each of which represents a particular operation or step in the algorithm. And the arrows represent the sequence in which the operations are implemented. Okay, so various blocks type. You know about this? So the starting and stopping of the program should have this type of symbol. And flow lines, how the information flows. Okay, so that gives the arrows. And a process, a rectangle. And input and output, that is write statement or print statement, they should be given in parallelograms. And decision, it should be given a rhombus or diamond. And the junction should be a circle. This is a circle actually. Okay, so if there is one flow coming from here and another flow coming here, and then it goes some other, and there is a junction, then it must be a circle, and off page connector, and it is going to another page after this, because my flowchart one page is not sufficient, then I will go like that. And the count control loop, so used for loops which repeat a prescribed number of iterations, I can use this. So these are various symbols that we use. Later I will show you some of the flowcharts. And then what is called a pseudocode. So as I told from before, high level language and between the flowchart, between these two, there will be what is called a pseudocode. It is an alternative way to express an algorithm that bridges the gap between flowchart and computer code. Again, anything problem? Okay. It's okay. And this technique used code-like statements in place of the graphical symbols of flowchart. Each flowchart symbol is put like a code through a code, but it's not exactly any particular high-level language. So it is something like this. So algorithm, flowchart, and pseudocode for the problem of adding two numbers. Two numbers are to be added. Begin. So this begin and end, it will be given like this. These are called ellipses. Okay, or it's like a rectangle with rounded ends. Okay, so this is called as ellipsis. And then input A, input B. There are two values I have to read. So these are given parallelogram symbols, input A, input B. And then these are to be added. So this is a process. So you add A to A and B and store in C. And C is to be printed. So output, again, it is like a parallelogram and it is end. So like this is what is called as flowchart. And these are various steps. This is algorithm. And this is pseudocode. Okay. So begin adder, input A, input B, C equal to A plus B, print A and adder. Okay. This is pseudocode. It cannot be executed in a computer, but it gives an understanding of what are the steps. Okay, and then this can be converted into high-level language. Input A means sometimes you may write statement WRAT, or sometimes you may put INPUT input or READ read. Based on the programming language, Fortran uses read. Okay, and C language uses CIN. Okay, and Fortran language is C language is uses fscanf, scanf, printf, those things. C++ use C in, C out, like that. So various languages have different commands, right? So we have to use that. But this is, by seeing this, I can easily convert it into high-level language. This is what is called a pseudocode. Am I clear?
Yes, sir.
Yeah, so top-down design example, a hierarchy of flowcharts dealing with the problem of determining a student's grade point average, right? How to calculate a GPA of a person, okay? So it provides a comprehensive plan, more detailed chart for a major module and detailed chart for a segment of the major module. So you can see this. I will not explain this. You can understand how it goes, okay? So here, this is the general algorithm. For that. So for each course, how to get it. So this is another. Again, this one to determine the average grade. So this is sub algorithm. So this is like top down. This is the smallest function. This is to be called by this particular one. So this is another function, bigger function, and one of the command it calls this particular function. And in this is the main program. Here, one of the command calls this function. Okay, so this function calls this sub function, like that. So this is from the top to down, how to design this. This is top-down design example. Okay, detailed flowchart for computing the average quiz grade. Okay, so one of this is elaborated there. That is this particular one, the small one is written here. And okay, what do you mean by structured design? And here, if you see in C language, suppose for loop you are typing. So for I equal to 1 to n, like that, if you put and enter, it will come with a indentation. Okay, so that it will give you, this is the structure. Okay, so each loop will be a structure. Each if will be a structure. Each switch case will be a structure. So you can understand structure by structure. So that will be easier to understand. But as I told, unstructured designs like Fortran, Basic and all, it will not give you that structure. Okay, so and there are standard structure, 3 types of structures it will use. And using those 3 structures, any program can be written. And the following are the rules to be followed by structured programming style. Program should consist solely of 3 fundamental control structures like sequence, selection, and repetition. Only these 3 types. And it is provided that any program can be constructed from all these 3 basic structures. And each of the structure must have only 1 entry and 1 exit. Okay, and there should not be, as I told, unconditional go to 25, go to 30, go to this statement, go to that statement. It should not be there. So then it is not structured. So that is the main restriction for structured design. Unconditional transfers or go tos must be avoided. If this facility is there, one go to statement is there, you can use it, but a good programmer should never use that. So it says unconditional transfers may result in a spaghetti algorithm, right? So when you have noodles like this, everything mingled, right? So the program will become like that. The structure must be clearly identified with component comments and visual devices such as indentation, blank lines, and blank spaces. Like every structure should be very, very clear and separate, so that I shall have to give comment. This particular structure will do this. This structure will do this. So I can understand from the algorithm each step how it is executed in the particular program. So the fundamental structures, as I told, one is sequence, means one instruction, another instruction, another instruction, another instruction, like that, sequential instructions. Okay, this is flowchart, and this is pseudocode, instruction 1, 2, 3, 4, like that. This is sequence. And then we have what is called selection, that is using if and if else structures. Okay, so this is selection type. So there is a condition, if this is true, it will do this, and otherwise it will go straight. Okay, it will do this and come and join here. And if else structure, if it is true, it will do this, otherwise it will do this, and then it goes like this. So this is the flowchart, and again this is pseudocode. If condition, then okay, true block and if. And here if condition, then true block, else false block, and it comes out. Okay, this is the pseudocode. So this is what is called as selection type of structure. And there is what is called as repetition kind of structure. Okay, block of it is to be repeated number of times. So there are various types like if then else ladder and switch case. Okay, so here if it is true, it will do it. If it is false, again it will check another condition, true or false. It is not repetition actually. It is like ladders. Okay, repetition, I think loops I will have. Okay, and so it will not, it is actually selection type only, right? This particular one, it is not repetition. Repetition comes later, which is a loop is repeated, it is not repeated. Okay, I should not put this here. This is just a else ladder and switch case. So these are the next thing. So maybe here I can put that. Okay. So repetition is like this. If a block of instructions is to be repeated, okay, do this block 1 till this condition is true. Okay, so this it goes like this. Do block 1, if condition is true, exit. Otherwise, it will do this block 2 and again goes here, and it will repeat like this. This is do loop. Okay, so as long as this condition is false, it will be doing. Once the condition is true, it will come out. This is what is called as do loop. And there are other loops also. Okay, this is here do for I equal to start, finish, step, and block and do. Okay, so it is like it starts from I is equal to 1 to n, like that. So if it starts from 1 till n, and with step you can give, okay, the step size here, like that. So this is do loop. And the other structures are there, like switch loop, switch case. Sorry, what are the other loops? While loop, do while loop, they are there. Okay, so there are sequence, selection, and repetition. Okay, so there is what is called as pre-test loop, mid-test loop, and post-test loop. So the testing can be at the beginning, the testing can be at the middle of the loop, or testing can be at the end of the loop to come out of the loop. Do you remember what is the difference between while and do while? Anybody?
Yes.
What is the difference?
Like while condition will occur only if the condition is true, but do while will occur for once if condition is true or not.
Yeah, it will test at the end. Okay, post test loop. Okay, that is, it will do it whether it is right or not. First it will do that loop, and then it will check whether it is to be repeated or not. And if it is not, then it comes out. So minimum once it will check, it will do that loop. But while loop, first check will be there. If the check is right, as long as that is right, that loop will be continued. Okay, so that is do while. And do so for loop will be for a fixed number of iterations if you know, right, ahead. So just recollect those things, whatever you learned in your C++. Okay, there are some more examples. And high-level language, as I told, basic, beginners, all-purpose, symbolic, instruction code. And okay, so whatever we are writing, it is called as high-level language. And the computer will not understand it. What computer understand? Which language it will understand?
Binary.
Binary language only. Okay, only zeros and ones. So these are to be converted. Okay, these are translators, right? And okay, the Fortran 77. Fortran means formula translation. And Pascal. Okay, this came from the scientist only, Pascal. And C, actually they have developed B language and then C language, like that. And C++, why plus plus given is, plus plus is like increment, right? So there is some incremental additions are there for to C. So that's why it is called as C++. And then MATLAB, which is a matrix laboratory. Okay, these are various languages, and so we can use either C++ or MATLAB. MATLAB, the advantage is, because as I was telling, we have to convert the partial differential equations into algebraic equations, which are a linear set of algebraic equations. And how can we solve them? In numerical methods, you have learned Gauss elimination, Gauss-Seidel methods, and all those things. So finally, you are going to get matrices. Those matrices are to be solved using Gauss elimination or Gauss-Seidel like things. So because we are going to deal with matrices, this MATLAB is the most efficient one to work with matrix. Okay, so if you want to add two matrices, you can give just A is a matrix, B is a matrix, A plus B you can give, A into B, A and B will be multiplied. But if in C++, if you want to add matrices or multiply matrices, you have to use either object-oriented programming or you have to write functions, right? You have to develop your own class and then you have to write the functions for that and organize. So MATLAB, it is not necessary. They are inbuilt classes and functions, so which can be used. Okay, so a pseudocode, how to convert into MATLAB. Okay, so this MATLAB syntaxes you can see. So this is the way you can convert into MATLAB. And then once you write it, so we have to debug. So there are various types of errors are there. Okay, so we have to execute. Okay. A program execution, okay, will have 3 steps. One is compiling, and 2 binding or linking, and 3 execution. Okay, I need actually a translator. Somehow these two are not linked properly. Okay, there are 2 types of translators. High-level language to machine language, which is binary code. Okay, this high-level language, we call it as whatever we write, this is called as source code. And this is called as object code. Okay, so this object code, whatever you write the program, it will be .c or .m. It is for CPP, like that. Okay, so C++ language, if you write, will give .cpp. If you write a MATLAB program, .m will give. Like this, what we call it as source code. That is to be converted into machine language, which is object code, and you will have the program generated by the computer .obc. Okay, there are 2 types of translators. Okay, one interpreter and another compiler. Anybody knows what is the difference between interpreter and compiler?
Interpreter executes the code line by line, and compiler first changes and executes later.
Yeah, very good. Thank you. So C++ is the interpreter or compiler?
Compiler, sir.
Yeah. So C++ it needs a compiler. But what about MATLAB? It is both interpreter and compiler. Right? So when you have the MATLAB installed, you will get like this. And suppose I give just like that, I will give root 75, okay, or something like 5 into 6, and enter. So it will give the solution. Immediately. I need not write a program to multiply 2 numbers. But if I want to multiply 2 numbers 5 into 6, I have to write a C++ code, and I have to compile it and then execute it. Am I clear?
Yes, sir.
So if you just give a command, it immediately executes in the MATLAB. That is called interpreter. And suppose I write a number of executions, some 10 lines are there. I have given some values and got executed. And I got the result. But I want to do the same thing again for different data. And again, I have to type all those things, right? So if it is only interpreter. But if I know that these lines are working well, and all these lines are clubbed together into a single program, and then I can execute it. It's like a compiler. Okay, so that is the difference between interpreter and compiler. And so here, the types of errors during compilation, so whatever errors we get are compiling errors, or sometimes we call it as syntax errors. And so we have to eliminate those errors. So it will give you, because it will understand, and it will give, once you execute, number of error commands will come, right? So by seeing that, okay, there is a particular line with this particular error, like that, you will have comments. And those comments are called as error diagnostics. Okay, so what, because it will understand these are the mistakes you might have done, right? It will give you the comments, and based on that, by seeing the error diagnostics, which gives the comments, you have to modify them. Okay, these are called compilation errors or syntax errors. And so, as I told, there are a number of modules we will write. Each will be compiled separately, and we avoid all the syntax and compiling errors. Then I have to combine all the modules, right? So that is called as linking or binding. So because this module may call some other functions written by another group, okay? In the function may be another module. And so that function will not be there in my module. And when all of them combine together, if one function is missing, then it will give you this particular one is not there or missing. So that is called as linking errors or binding errors. So this also will get error diagnostics. I can eliminate them. And then once you do that, I will get what is called as exe file, executable file. Okay, so this executable file, once I get, I can run it. Okay, so that is called as execution. And again, you may get some errors. These are called as execution errors. Like as I told, when it is calculating, divide by 0 may come, right? Or a root under a negative value under a root may come. Okay, such errors, execution errors, and these are called as runtime errors. The errors that we get during runtime. Okay, this also will be given as error diagnostics. So all these things can be eliminated, and finally I get a solution. Okay, so even then, if I get a wrong solution, so there are still type of errors are there. What are these errors? These are called as logic errors. And computer cannot give, right? Error diagnostics cannot indicate logic errors. Logic errors means error in maybe formulation, right? Maybe formulation or your logical implementation. Okay, so you have to check. So this will not be given by the computer, and you have to find out. Okay, so these are the things. Syntax errors during compilation phase violates the rules of the language, such as spelling, number formation, and other conventions. These errors will be indicated during the compiling through error diagnostics. And missing parentheses, missing semicolon, printing undefined variable, like this, these are all called compiling errors. And the link or build errors. And during the linking phase, and so like misspelled name of a function, like what it says is unresolved external reference. That is, externally you have referred for one function, it is unresolved, like that. So these types of errors are called as link errors or build errors. Then runtime errors like divide by 0, square root of a negative number, floating overflow, right? Number of like e power 50 or something is coming, then 10 power 50 like that, it is what is called as floating overflow. Then logical errors due to faulty programming logic will not be indicated in error diagnostics, like infinite loop, wrong formulation, etc. Okay, so these are various errors which are to be eliminated. What happens if one of the following happen when an error occurs? Okay, so when an error occurs, what happens? An explicit diagnostic can provide you with an exact location and the nature of the error. And a diagnostic may occur, but the exact location of the error is unclear. or no diagnostics occur, but the program does not operate properly. These are the things you may get. So we have to debug in one of the following ways. How to do this? How to debug it? So your efficiency depends on the debugging the program. Okay, writing a program and is not a big thing, right? And error diagnostics elimination also not a big thing, but finding out the error, logic error. Okay, so what I have to do, print out intermediate results. So normally one rough calculation I have to do. And so that you give one particular data, if you do it, and you give that data as input and see at different steps what it is giving. Okay, you can check the values. Like when I am correcting a paper, the solution of a problem, like a turbo machine problem, suppose, I will see up to what point you have done right and where from where you have done wrong. So I can find out exactly where the error is. And locate the module with error by printing results at the entry and exit of each module. And debug independent modules before integrating them. And scan the code line by line, doing calculation and checking the values to identify the exact location of the error. And check from the beginning, formulation of the problem itself. It's not enough if you just see the program. And the formulation itself may be wrong. At the beginning itself, it may be wrong. So that you have to check. The boundary conditions that I have taken may be wrong. Right? So then testing. One of the greatest misconceptions of the novice programmer is the belief that if a program runs and prints out results, the job is done. Okay, that's what people think, but it's not right? It is to be tested. The results may be completely incorrect. The results may appear to be reasonable, but are in fact wrong. And the results may be qualitatively correct, but quantitatively wrong. Okay, so to ensure that such cases do not occur, the program must be subjected to a battery of tests for which the correct answer is known beforehand. So what are the phases of testing? Module tests, development tests, whole system test, and operational test. So module test, test module by module, we have to test it. And development test, they are implemented as the modules are integrated into one single program, total program package. A test is performed after each module is integrated with a top-down approach. Okay, and that starts with the first module and progresses down through the program in execution sequence. And whole system tests. After the total program has been assembled, it is subjected to a series of whole system tests by exposing them to, first we have to test with the typical data, and then I have to test with unusual but valid data. And then I have to test with incorrect data also to check the program's error handling capabilities. So if it is incorrect data, it has to handle that and it has to give me proper comments. The user has to get proper indication, right? So that testing also I have to do. And this is called as alpha testing. And then beta testing, what we do is normally you will get a new package, beta version will be released free to all the people. So you can just get it and work it without buying. So why they do it is, so because lakhs of people may work with different data, and if those people are getting some problem, they will contact these people, right? And say, this is not working for my data. And what is the problem? They will ask and they will try to eliminate them. So that is called as beta testing, to test how the program runs in a realistic setting. A standard way is to have the ultimate user to implement the program. And then I have to use the proper documentation, as I told, manual writing and all. Sufficient documentation is to be included into allowing the users to immediately understand the program and how it can be implemented. It needs internal documentation and external documentation. What is internal documentation? So that program should be readable. I have to have proper comments in between, proper blank spaces in between, like that. So include module at the end, head of the program, giving the program's title. At the beginning, you give the title, your name, date, and what it does, all those things. And include a second module to define each of the key variables. Whatever variables we are using, all of them are to be defined. It is like nomenclature in your project work. And then select the variable names that are reflective of the type of information of the variable to store. And insert spaces within the statements to make them easier to read. And use comment statements liberally throughout the program, right? So I should understand what next step is going on, what is it going to do, like that. So, and to skip lines for the purpose of labeling, clarity, and separation of modules. In particular, use comment statements to clearly label and set off all the modules, and use indentation to clarify the program structure, in particular to set off loops and decisions. Okay. So this is internal documentation. External documentation is like manuals. This refers to instructions in the form of output messages. The result that we get from the program, that is output or post-processing, they are external documents. Okay, output messages and supplementary printed matter. The messages occur when the program runs and are intended to make the output attractive and user-friendly. This is external documentation. And this involves effective use of spaces, blank lines, special characters, etc. to eliminate the logical sequence of structure of the program results. So results should be, if it is printed, tabulated properly and give the names of the each column and all, it is to be done properly. And the program can design the output descriptive error messages to alert and inform the user regarding problems. That is, if there is an error handling, I told, right? If there is some problem is coming, it has to indicate immediately to me. So whatever user getting as comments or results, right? They're all external documentation. Not only that, the making of a comprehensive user manual also is a external documentation. Then
Sir?
storage and yes.
Sir, time is running out. We are running out.
Yeah, it's ending, like the last step, storage
Okay.
and maintenance. So when you sign off the computer, your active file will be destroyed. To retain the program for later use, you must transfer it to a secondary storage device such as a hard disk. So I should now, many times what happen is, sometimes if suddenly crashes, I lose all the data. Some power cut, all the data will be lost. But it should not be like that, right? So even if power is lost, the program should be able to continue after some time when the power comes back. And other major tasks like upgrading the program in light of experience to gather feedback regarding suggested improvements in design. That's what I told. You have to, in beta testing, I get feedback from the users and I can upgrade it. And ensuring that the program is safely stored. A backup copy should always be created before making major code changes. Okay, so these are the things we have to be careful in software development, I think, right? So you go through that chapter, second chapter in numerical methods by Chopra. So the same thing is given here, and you can see the examples and all. And okay, another thing, because you are with Gupta sir, this weekly test will be there, right? So when can we have that slot?
Saturday, sir.
Saturday, eh?
Sir, no, sir. Saturday we want holiday.
Okay.
So Friday evening would be
Friday
fine.
evening.
Yes. Friday evening or Monday evening, anything will be fine, sir.
I think Monday evening we will keep it.
Yes, sir. Monday evening would be.
Yes, sir.
Okay.
Monday.
Because Saturday, Friday evening also sometimes we'll have weekend programs or something. Okay.
Yes.
So we'll have Monday evening.
Okay, sir.
Okay. So if it is not there, I will tell you. Otherwise, you just expect a test on that day.
Okay, sir.
Okay, sir.
Right?
So do we have this week, sir? I mean next Monday.
That's what I will tell you if I can. Because now it is online, I have to spend a lot of time to make the test paper or something, right? So I will see if my time is sufficient. I will have it. We will have it. Otherwise, no.
Okay.
Okay. So assume that it is there. If it is not there, okay, be happy, or it can be some other day. Okay. Okay, I think story time may not be there. You will have. What is the next class?
HMT.
Eat and master.
Okay, then. See you then. We will not have story today. Okay, so see you. Thank you very much.
Thank you, sir.
Any suggestions, any problems, you just ask me at the beginning, as I told repeatedly, right? Don't be sit with problem and finally worry about it at the end of the semester. Okay, see you. Bye.
Recording stops, yes.
Yeah.